And I have a pleasure to welcoming Karol Lang, a professor from University of Texas at Austin. He will talk about image-guided flash proton therapy. And Karol Lang has finished his studies at the University of Warsaw, Faculty of Physics, in the old buildings, long time ago. And he got his master thesis under the supervision of Helena Białkowska. And after this thesis, he went to the US, to University of Oxford,
Rochester.
Texas at Austin.
Yeah,
Rochester,
Rochester.
that's right. And he got his PhD under supervision of Ali Podek. And he's a particle physicist working in various experiments in particle physics. And maybe I can just say a few words about it. So he's a professor of physics at the University of Texas at Austin, where he teaches and conducts the research. And he was participated in many experiments. Let me just say a few at Fermilab, SLAC, Brookhaven, and recently at CERN. And currently he participates in the Fermilab program to study neutrino oscillations and experiments designed to search for neutrino-less double beta decay. And he got also interested in applications of experimental methods used or developed in experimental particle physics to medicine, and in particular using image-guided flash to proton therapy. So the floor is yours. Thank you.
Thank you. Thank you very much. It's a great pleasure to be here, and I thank you very much for inviting me to give this talk. As some of you know, this is a sort of a, maybe not a repeat, but a follow-on on the talk that I gave, in fact, the last couple of years as a seminar in here. And since our research continues, there's maybe a little bit of news that I will try to report today. So it's really a great pleasure to see colleagues and professors that I have taken classes from, and just be back, not in the building because I was never here, but be among old friends. The image-guided flash proton therapy is probably a little bit a cryptic title, and I will try to decipher it for you as I move along. I will start with something that I call a big picture. Okay. And I have actually two introductions about our background and what proton therapy actually is. Then I'll talk about what we have done and perhaps where we would like to go in the future. So let me start with this, what I call a big picture. There are two sober facts that 18 million new cancer cases per year happen worldwide. 50% of patients receive radiation treatment. The question is, can we apply radiation treatment better? Now, what does better mean? Better can mean minimize or avoid post-radiation complications, usually referred to as toxicity. Treat more patients with protons, because as you will see, the range, the number of patients that can be treated is actually very small until now. And can we lower the cost of therapy? And this list can probably continue depending on points of view and what would you like to focus on. But in general, the idea is, can we make things better for patients and treat more patients? So I will start by reminding you what Yannick just said, that I am experimental particle physicist. I've been conducting experiments. And I have this sort of popular slide which captures what we have been all working on for the last 3-4 decades, depends how you count, where particle physics, discovered completeness of the standard model, which as we know is not a complete theory, and how it beautifully placed together with cosmology and the evolution of the universe. And these two pictures essentially capture these achievements. Now, we have answered many questions and solved many puzzles, and at the same time, we discovered new, maybe even more fundamental questions and puzzles, which are listed here, and I'm not going to go through them because everybody sort of knows them, and those of you who do not know, that would be probably too cryptic anyways. You always can ask me after the talk. But there are big questions about the evolution of the universe, the asymmetry of matter and antimatter in the observed universe. What is dark energy? What is dark matter? And the list is long, and again, you can add to what I listed there more. And amazingly, quite amazingly, neutrinos seem to play quite a fundamental role in perhaps answering many of these questions. They're, as I say here, implicated in some solutions to some or maybe all of these puzzles. They are ingredient of these future solutions. So this is why, in fact, I was motivated to work on experiments in neutrinos, and I happened to work on two quite distinct fields in neutrino studies, namely neutrino oscillations program at Fermilab and neutrinoless double beta decay, which is a nuclear physics, essentially, technique currently in Gran Sasso. So, in order to conduct these experiments, we build the detectors, and these are pictures of some of the detectors that we built in our labs. And I will not dwell on that, but about 25 years ago, we also were thinking about medical instruments, and specifically positron emission tomography. So based on our original so-called tracking detectors, so-called straw drift chambers that we built for some experiments at Brookhaven, we had an idea that perhaps we could apply this technique or technology in general to actually construct something pixel-like response to gamma rays that would be coming from the positron emission, and reconstruct what you would call tomography. This was very naive, by the way, never worked, but just to indicate that even 25 years ago, I had some angle from which I was looking at the issue. Many of these ideas, by the way, can be credited to Georges Charpak, who some of you know very well. And this is a picture in which I counted 4 members of the local group who have, and I will not point to faces, you can find yourself there, Wojtek. And George Charpak, interestingly said, when I saw groups with more than 1,000 physicists, I became scared. So I decided to switch to the application of my detectors to medicine and biology. I'm not sure that I would express it in a similar way, but nevertheless, it's a sort of valid point. There's a certain scaling difference between medical devices and particle physics experiments, which, as we all know, have become huge. And so, as I say, we are working on the shoulder of giants because even the biggest figures in this field did have an eye on applying what we developed for particle physics to actually social applications or humanities in general. So just going towards what we have been doing at Fermilab, I don't want to dwell on this, but one of the experiments that searches for neutrino oscillation is this experiment that is now essentially completed. Was called MINOS, and we were sending, this is aerial view of Fermilab. There are 2 accelerators. This one was producing neutrinos that were sent 730 kilometers to the Earth, and we were measuring flux of neutrinos in the near detector and the far detector, and by comparing the two spectra, you can actually measure some of the oscillation parameters of neutrinos. This is the same Fermilab that I showed on the previous slide. This is aerial. Essentially, if you flying to Chicago from the west, 10 minutes before you land at O'Hare in Chicago, you can actually see this quite clearly, because obviously these rings are very characteristic structures on the surface of the Earth. And among them, there's this high-rise, which is a tall building and the only tall structure in the Illinois prairie. This is inside this building in the middle, and this is, again, this building in the close-up. And this building was, by the way, designed by the first director, Robert Wilson. Robert Wilson not only designed, but he essentially was the director for the first 10 years of Fermilab, which, as you may recall, was essentially the #1 laboratory in the world back then. So in our neutrino experiments, we measure neutrinos, we measure neutrino oscillations, we measure events. And this is an image of a neutrino event. So we are dealing with imaging even in such huge experiments, and this is an example. And by looking at different features of these hits in the detectors, we can actually we can extract information about neutrino interactions. So you can observe a lot by watching. This is so-called Yogi Bearism, which fall very flat in Europe because nobody knows who Yogi Berra was. So I will skip that. So this was my first introduction. The second introduction is about proton therapy. So the reason I was talking about Robert Wilson, besides the fact that he was close to my past history, was that in 1946, he wrote a seminal paper about proton therapy. In this paper, 1946, he wrote that protons, unlike gammas that people were using already back then for various medical applications, propagate through bodies very nearly in a straight line, and they deposit strictly localized energy in strictly localized region, and soon this will be feasible to actually shoot sufficiently large energy beams through bodies. So in 1946, the highest energy achieved by accelerators was of the order of 150 MeV. In Wilson's paper, there are these two figures, and this is the energy deposition, and this is the energy penetration of protons. And this is sort of a modern rendering of it. So I prefer to look at this because this is actually hard to decipher. So this is what protons do, and there's what we now know, a Bragg peak. Interestingly enough, Wilson never mentioned in his paper the name Bragg as the principle behind his statements. I don't know why, but he didn't. And we know that this is actually the crucial importance and crucial difference between protons depositing energy and precisely ranging out where they exhaust their energy, and gammas or X-rays, which keep on basically propagating through materials, including bodies. So localization of the beam energy is very, very precise with protons and very fuzzy, damaging when you actually use X-rays. So just a reminder, this is the same image about stopping energy in the water this time. So this is protons, which deposit a little bit of energy, ionizations, as they propagate through matter, and then this is in water, and then dump most of its energy at the very end. And this is gammas. They just shower through the entire track where they are exhausting their energy. And again, these are the two Braggs, father and son, who got the Nobel Prize, not for the Bragg peak, who was discovered by William Henry, and this is more or less his plot from 1903. They got a Nobel Prize a little bit later. So these beams are available in few centers in the world. I will get to it in just a moment. But one of them is so-called MD Anderson Cancer Center, and there's something called Proton Therapy Center, where there is a synchrotron which delivers beam into 3 stations where there are patients. In fact, 4, and I'll come back to this, but this is lower energy beam. These are a little bit essentially full energy beams of up to 250 megaelectronvolts. This is essentially the energy of all modern either cyclotrons or synchrotrons. Now, when I started working with this group, I said, this is one of the worst illustrations of what you have in your facility, because it really doesn't show the scale of what you have. And so I looked online for better illustration, and I found a Florida Proton Center illustration, which a lot better illustrates the complexity and the scale of such devices. Specifically, in Florida, they are using cyclotrons, so this is not a synchrotron, but the rest of the facility is effectively the same. So these beams are delivered to 3 so-called gantries, and look at the size of these gantries by recognizing that this is the size of a patient. So this 250 GeV has to be delivered at different angles and different, perhaps also energies, and they rotate depending on the angle and position through these gantries. So this is a major structure. In fact, you would think that it's where most of the cost of the facilities. Turns out that most of the facility, cost of most of facility is actually in civil construction. It's because of the stability necessary for delivering the beam. It's because of the radiation shielding. So roughly speaking, out of $200 million, which such a center costs, 150 goes into civil construction. So all of this is just a quarter of the rest, of the total world. So what's coming back to how protons and electrons or gammas differ in irradiations. On the right-hand side, it's very poorly, for some reason, very poorly focused. I don't know why. The beam is delivered typically in spots or so-called beamlets. So the extraction from the accelerator happens in about between 1,000 and 5,000 spots. And these spots are adjusted in such a way that energy deposited conforms to the cancer tissue where you want to deposit the energy. This is impossible for gammas. Gammas basically just plow through the body, and the advantage here is that there's no damage of the tissue past where the beam deposits all the energy. Here is just basically damages organs that are behind the cancer tissue. So there's a huge difference, and it's an essential difference between protons and gammas. So this is, remember the Bragg peak, which is one of these beams is like this. But if you change energy and you change the direction, you can achieve so-called spread out Bragg peak, which is more in 3 dimensions, carving out or depositing the energy into the cancer tissue. So this is, again, for the so-called intensity modulated proton beam, it's about 1,000 to 5,000 spots that are happening over a few seconds or a few tens of seconds. Once again, illustrating the difference, protons stop, gammas don't, and similarly here. Essentially, the more color in this right-hand side you see, the worse it is. This is where the toxicity actually is occurring. So protons are fairly well concentrated, gammas damage beyond cancer tissues. There are only 122 facilities worldwide delivering proton beams. This is what it is in the map taken from a very nice website, PTCOG, which has all kinds of information, and in fact, you can read about every one of these centers, and there are very small number of centers in the southern hemisphere, namely it's 0. In the upper hemisphere, northern hemisphere, there are the countries with the largest number of centers are in the US, Japan, and then in Europe, in Germany, China, and as you know, perhaps, there's one center in Poland, in Krakow, in so-called CCB. In my state of Texas, there are 3, and there's one more coming soon to the capital of Texas, Austin, where I live. So this is the statistics of patients that have been irradiated using these beams worldwide. Now, this is starting at 2007, going to 2022. This is again from PTCOG. And as you see, the number of patients irradiated with protons is reaching about 300,000. This is integrated number of all the patients, cancer patients, throughout the world. I mean, it's an amazingly small number. However, it's growing. So I drew this reference line, straight line, to emphasize that there is a, maybe not exponential, but a fast growth of the number of centers in the world. In fact, in Europe, there was an announcement that 10 centers will be built in Spain. 10 centers in one country. China is building 10. And altogether in the world, there's about 100 more. So I told you, 122 is currently in use. Around another 100 are being either planned or in various stages of construction. So this is recognized as an important way of treating patients, and unfortunately the costs of these facilities does not allow to have quickly the growth of it to match anywhere near what is available through gamma therapy. So a natural question would be, so 122 proton centers, how many gamma centers there are in the world? And the answer is there are various gamma centers, but to be a sort of generous in various ways that these treatments are administered, it's about 21,000. Okay, so there's 200 times different in number of places where the cancer can be treated through gammas. Proton treatment is a very well-defined process which starts with about a week being taken for planning. So there's a team of people who import images from positive emission tomography, from MRIs, from CT, from all other aspects that a patient might have been measured and treated. And there's all kinds of simulations involved and related to it, planning of what energies, what directions, beams are needed to actually carve out the cancer tissue with protons. So there's, the process was described to me as starting on Monday morning, there's a team of 4 or 5 people, including a physician. And on Friday, the process is being reviewed, treatment plan is established. On Monday, a patient shows up and goes through 30 irradiations day by day. That's the current standard protocol of applying it. Unfortunately, this is more or less the end of good news. So protons are great. However, there are limitations how they are or can be used. And the reason is that we are not the same. If you look around, your neighbor doesn't look like you. And her organs also are different. So obviously that relates to limitations of how I can, or we can use the imaging, how we can use the knowledge gained in irradiations from earlier irradiations using gammas. And the list is long. I don't want to tell you all of this, but there are certain limits which primarily can be pointed to the fact that would benefit from better monitoring how the energy is actually deposited into the tissues. So this team of 4 or 5 people who work for an entire week, it's not obviously on one patient for a week, but it takes a week to reach the treatment plan. But this team would be probably the first one to tell you that there's much room for improved feedback. And in fact, I've heard this directly stated to me. However, it's complicated. But this is sort of the direction that we are thinking of. The question, a natural question, how does radiation work in eradicating cancer? It's actually a very good question, not for physicists. When I ask physicists, they always give the wrong answer because they don't know chemistry. Most of physicists don't know chemistry, biochemistry. This illustration, I don't want to pretend that I know much about it, but I'll mention where the issues really lie. So there are different processes that radiation is impacting the live tissue. One of them is essentially just direct damage by charged particles of DNA strand. There is creation of all kinds of oxygen radicals, something that is usually referred to in chemistry as ROS, reactive oxygen species, which are essential, turns out, in interacting with the not only DNA, but lots of other elements in cells. And these elements, this chemistry, besides maybe this physics, the rest is chemistry, is on different time scales. So starts from femtoseconds, goes to microseconds, and the question is, do we really understand it so well that we can, with confidence, state how we apply, when we apply protons or gammas, that we understand how the cancer is eradicated? I will leave this question hanging, and I'll come back to it, but you can start guessing what the answer is. So this is an illustration that there are theoretical actually calculations. This is animation that is showing this OH, which is sucking out another hydrogen from either a DNA strand or from whatever environment it happens to be. OH, or in general, oxygen radicals, are extremely important, extremely reactive, and they are at the core of problem related to the deposition of energy. It should be also here. This is, okay. So again, you saw that this OH group sucked out a hydrogen. And there's more of this happening, and I'll come back to this a little bit later. So this was the introduction. Now I can maybe get into what we have been doing. So I'll accelerate a little bit because now things are really very simple. 5 years ago, I was approached and asked to, and it was proposed to me, how about if we build a positron emission tomography scanner to provide a feedback for proton therapy? And I must confess that 5 years ago, I knew very little about all of this that I told you. And specifically, I've heard about proton therapy, but how it's used, what it's used for, what's the difference. Of course, I knew Bragg peak and I knew gammas. These are, particle physicists obviously use it experimentally all the time. But how it's actually being applied in medicine was certainly very new to me. So before I tell you about what we did, a brief reminder what positron emission tomography is all about. So forget about the beam, because that's not how positron emission tomography scanners were invented. They were invented by essentially looking at injected radiopharmaceuticals into a body. And these were radiopharmaceuticals that are beta plus emitters, in other words, positron emitters. So a positron is annihilated with electrons in the tissue, and it creates two photons, which create effectively the so-called line of response. So these two detectors, if you put them on opposite sides of where annihilation happened, produce so-called back-to-back photons, which essentially comes from the conservation of energy and momentum. So a detector, a conceptual detector can be, well, in the first detector that I showed you, actually, it was not based on this principle, because I was actually, with our xenon straw chambers, we were actually thinking of capturing gammas in a different way. But typical nowadays, a way to do it is actually using a scintillator where you convert photons into light and detect it with a photodetector. And this is more efficient, this is much denser medium, and that's why it's better. So as I say, what we did 25 years ago was quite naive, but back then the state of the art was very different, so I could probably justify it a little bit better why we did what we did. So here's an image from a PET. If you inject into a patient radioactive sugar, which has fluor 18 as the marker, this is what PET scanner is showing. And there's two characteristic things. One is this spot, and one is this spot. This spot everybody knows, it's a bladder, it's our garbage disposal. Well, this is a cancer. This is where metabolism is increased, and increased metabolism ends up with the increased number of positron emissions. So if you improve your detector from left to right by having no time of flight to having time of flight, which I will probably not discuss much, but this is something that improves the signal to noise, improves the time response of the detector, you can actually make it a little bit crisper and thus more sensitive to capturing, to actually imaging, and in fact dosimetry of cancer tissue. So in our case, when I was approached 5 years ago, it was not to just use PET scanner as a device to detect radiopharmaceutical, but actually exploit natural activation of body when proton therapy is happening. In proton therapy, nuclear fragmentations or nuclear so-called PN reactions are leading to creation of, for example, of oxygen-15 or carbon-11 or nitrogen-13 that live very short times. These are half-lives of 20 minutes, 10 minutes, 120 seconds. I will show you actually also carbon-10 that we later detected. Carbon-10 lives 20 seconds. So these irradiations, when the proton beam strikes the tumor, create activation, create these isotopes, regardless whether we're looking or not. So we essentially, the idea was, so why don't you look and that, by measuring its dosimetry and imaging, would provide feedback of, have we done it right? Perhaps we could correct it for the future. That's the principle with which we wrote the proposal, and we illustrated it by simulations which show, by the way, this is the Bragg peak, but positron emissions are not happening where protons exhaust their energy. The energy dependence of the cross-sections for creating the isotopes that beta plus emit happens actually all along the entry into the tissue or into the body, and are created throughout and essentially peter out at the end where there is no energy, so nothing can be, the beam cannot create beta pluses anymore. So one has to keep it in mind that this imaging that we are doing in this way needs to be accounting for this difference. This is quite an essential feature because obviously you don't want to pretend that this is where most of energy is. This is where most of energy is. But through simulations, that are very well-known connections, so one can actually do that. So this is a proposal. We started with these ideas, and we ultimately designed it to be this way. And interestingly enough, it was funded by the government of Portugal. It's a very strange concept. I hadn't known about it when I was approached to write this proposal, but it turns out that the government of Portugal has agreements with some universities in the US, perhaps somewhere else as well. I'm not in the Portuguese government, so I cannot testify to what they do. But among them, there's University of Texas, where they have, so University of Texas gives some money, government of Portugal gives some money. They have funds, and people can apply, and yearly they announce various topics for applications. And that year it was actually on sort of medical devices. We wrote the proposal, and it was judged to be the #1 proposal in the competition. So I had collaborators from Portugal. There was a commercial company, Petsus Electronics, that produces essentially the electronic readout. Our group, there was a group from MD Anderson, and 3 groups from Portugal. I want to mention, just so I'm not accused of being arrogant, although you can accuse me of it anyways, that the idea of monitoring is nothing new. In fact, there's a paper, this is 2004, which had charge hadron tumor therapy monitoring by means of PET. However, as you know, 20 years ago, technology was different. The ideas were different. And this was not fully what we are thinking of having the SPECT scanner in the beam so that we are sensitive to these very short-lived isotopes. In fact, this particular paper conducted at GSI this was a study for 7 years, and mostly, in fact, if not only with carbon beams, not even protons beamed by carbon beams, which, in addition to Bragg peak, have other complications, and I will leave it undiscussed, perhaps. So we got approved when the COVID hit. But amazingly, we were able to advance our project nevertheless, but only 2 years into the project, we were able to actually go into the center where we are planning to use the beam and measure for the first time, will it fit? Is that the environment that we've seen in drawings and all of that? So this is what my student and engineer are doing here. And these are the components out of which we built our scanner. So you will see pictures of it. Very briefly, there are scintillating crystals, 3 by 3 by 15 millimeters, coupled to the photodetector, the so-called silicon photomultiplier, and then the rest is the electronic readout, in fact provided by this commercial partner that worked with us. And these are some pictures. So this is, again, SIPIM, so-called silicon photomultiplier, SIPIM. These are so-called LISO crystals. They're very dense, very luminous. And this is a fundamental module out of which we actually built our scanner. So not 8 by 8, but actually 2 times 8 by 8. So this is 128 channels. And the electronic readout was working very well from essentially day one, with some hiccups here and there. And this is a full chain, which I will not discuss because it's a little bit complicated. So we built, as we were building these modules, which were the fundamental bricks, I call it the Lego blocks of our PET scanner. Okay, I'm halfway through. So I'm going to accelerate. We measured every module, and we measured its energy dependence and energy response, and these are the so-called photo peaks, where the full energy is deposited, and timing. And when we go to distributions of the timing, we are achieving 229 picoseconds. Commercial systems are of the order of 250, so this is better. But if we actually select the best so-called line of responses, we can achieve 180 picoseconds, so that's nothing to sneeze on. So I need to accelerate, and I will show you devices how they work. So this is what the entire scanner looks like. And we then took a radioactive source. This is a germanium-68 source that we can use for calibration. And when we do it, we can actually go in a circle and look at the response of the scanner. So you're looking here at half an hour of the scanning around the circle, which are compressed here to just a few seconds. We can do the same thing with lines. So this is now going along this direction. And again, we can do also in the opposite direction. And you have these lines which illustrate how we can reconstruct the imaging or the images. As we were building our detectors, we were thinking about some other things. And one of them was, well, the scanner that we built was small and full of holes. So why? For two reasons. Maybe primarily one. Lack of funds. This is expensive. So we actually lied and say, well, that's because we need to deliver the beam, so it needs to look this way. But it's, in fact, one would like to have more a scanner that would look like this. So there would be actually very hermetically enclosing the body. And then one can imagine that you would have a special beds on which the patients would have different ways. Now, there's one important subject that now essentially occupies our thoughts most of the time, which is called the flash effect. Now, I need to spend a little bit of time, but I'll try to be fast. So, in conventional treatment, as I told you, there's about 30 treatments day by day. It's about 2 grays per day. 1 gray is 1 joule per kilogram. Now, recently, people have perhaps rediscovered, it's actually a jury's out whether it's true or not, And turns out that if you compress the entire treatment from 30 days to just one shot, and only compress it to one shot, but also rather than using 30, 40, 50 seconds, you have actually a fraction of a second. So you're compressing into instantaneous rates which are of the order of 1,000 times higher than in the conventional irradiation. Two miracles happen. One is that the effective eradication of cancer is the same as spread out over 30 days, but sparing of the healthy tissue is better. So, needless to say, this is such a hot news in this field that if you Google flash therapy, or flash effect as it's called, it's all, the conferences upon conferences, workshops upon workshops that are focusing on that. But you can ask, so how come? Why is it rediscovered? Why is it discovered? Why didn't we predict it? So I call it that there's an unescapable conclusion that we are missing some fundamentals in our understanding how radiation is actually acting on a live tissue. And perhaps a large fraction of radiation patients can receive a better treatment. There are theoretical modeling, believe it or not, there are fantastic chemical codes that actually show how you can, going back to our radicals, how you can actually be working with either conventional on the left or flash on the right, where flash means a lot more activity because per unit time, there's a lot more energy, a lot more radicals. So there's my new collaborator, Ramin Abolfat, who is actually conducting these interesting theoretical calculations. But as we were looking at this, we said, well, can we do something about it? So we actually conducted two experiments. And these two experiments were conducted about a year ago in the ocular beam. By the way, let me go back and only say that our first paper that was published about a year ago has more than 2,500 downloads. So that's actually, now I can brag that this is quite good. And we went to this ocular beam, so one of the smaller beams, but this is the only place where flash is applied in MD Anderson. We positioned just two of these modules. This is one module, this is another module like this, and this is a phantom. This is a piece of plastic. Acrylic turns out to be, by average, very similar to our bodies in its content of carbon, hydrogen, and oxygen. So we took a 100 millisecond beam spill. In fact, my group took 3 of those shots, 1, 2, 3. And we measured the response, energy response. Here are the 2 photo peaks from the line of response. This is for 3 different channels. And unfortunately, when we looked at what was happening during the spill, during the 100 millisecond, we discovered that something was very bad, and there was nothing. Our electronic was dead-timed. Turned out that there was a mistake. Nevertheless, we used 3 minutes of data, 3 shots. The experiment lasted whopping 10 minutes. And we created images. And these images are shown here. So these are from 3 different views. It all very well agreed with simulations, showed something that I showed you before. But from actual measurements, we actually observed carbon 10, 11, oxygen 15, and actually we cannot find nitrogen 13. But this describes the sort of latter part of the spill very well. Initial part does not, because we likely are missing some isotopes that are not accounted for in our analysis. But because of this dead time and essentially the importance of looking within the spill forced us to go again to MD Anderson. So we went there 6 weeks later. We did the same thing, but with various improvements. And Now we took data for 20 minutes and with 6 different phantoms. And this is the spill, which I'll show you in just a second, has so-called prompt gammas. And this is 20 minutes of data, positron emission, that we are recording in our devices. And when we look during the spill or in spill, the 100 milliseconds, this is the spectrum of gamma. And we looked in the post-spill where beta plus occurs, we see clearly the photopeak and response as expected. And this is, on the left, is basically just the sum of the two. Not only that, during the spill, we can, from the randoms, we can, in fact, measure the intensity of the beam, which is provided to us by the accelerator anyways, and agree very well. So one is, in the 3 different spills, one is from the accelerator, the other curve is from our randoms. And it actually agrees well. We simulated this. It works very nicely. We measured the isotopic abundance as the beam penetrates into the phantom. So if you look closely here, in this illustration, this is the phantom, this is the beam, and we divided our detector into some subsections which were selecting the area or the volume from which positrons were emitted, and this goes this is shallow, this is deeper, and this is the highest depth that we were able to measure. And we conducted a measurement of this abundance and have detected, like before, carbon 10, 11, oxygen 15, and still cannot find nitrogen 13, and I have no idea why. But this is quite amazing. Nobody has, to our amazement, nobody has conducted such experiments. Nobody has measured the abundance of isotopes by PET this way, and certainly not in the beam. So this is for 3 different phantoms: acrylic, PMMA, high-density polyethylene, and water. And we took 20 minutes of data, so we now can actually show dynamically the animation of data as they propagate, as the gammas propagate. And on the right, you see dosimetry, in other words, count rate. So we are measuring what's happening, and we are seeing what's happening in these. And remember, this is not a big detector. This is just 2 modules, 2 tiny modules. So many things. Now, as we look through this, as we think about what can be done, we've conducted a sort of a wish list, or assembled a wish list, which essentially touches upon all aspects of the therapy. We can do better detector. We can, in fact, improve pharmaceuticals. So I didn't tell you that we are using any pharmaceuticals. We're not using any pharmaceuticals, but one can actually inject something that would enhance the imaging of positron emission. So there's lots of things, in addition to new software, new protocols, and cheaper and better beams. So essentially, you can do a do loop of all the features of the treatment to improve all of that, and nobody wants to listen to this because it's just too disruptive. But we push along, so we've written some proposals. In fact, we want to measure not only positrons, but we want to measure these within this 100 milliseconds, so-called prompt gammas. These are the gammas that are emitted immediately as the beam is delivered to the nucleus, and have ideas of how to construct a scanner that would, in fact, be sensitive to such gammas, and we're sort of working on it. So if I have 1 more minute, thank you, and I apologize for running over. Let me just give you what I call an initial thought, although this is perhaps the concluding remark. In particle physics, we work in large groups, and these are some of my colleagues on some of the experiments that I participated over the last few decades. So different names, different groups, some of them, in fact, in front of one of the buildings in Austin. 8 years ago now, my university announced a campaign for interdisciplinary science. And they said, if you're interested, write a 2-page note in which you would answer 5 questions, how to engage your perhaps interested colleagues that would bring something that you do not have in your lab and have interdisciplinary research and development. So I thought about this and I wrote a note. Let me point out, this was 8 years ago, which was called Development and Demonstration of 5-Dimensional Positive Emission Tomography. I answered some questions. It was obviously not understood at all, found no traction in campus. Very many fuzzy things did find traction, but not technical ideas like this one. But I want to point out to one thought that I had there, which I showed to several of my colleagues, and they said, you should be showing this when you give your talk. So this is sort of in response, by popular demand, I'm showing you this thing, and I'm going to read it because I carefully edited it, so I don't want to screw it up. So here it goes. Can an effective collaboration be formed, modeled on research projects in experimental particle physics, that would accomplish in nuclear medical imaging what has not been accomplished over the last few decades by a number of small and isolated groups worldwide? Now, I wrote this knowing already then, because I was reaching out to various people, that in medical physics, there are tiny groups that are typically years behind in technology, years behind in understanding what needs to be done, and are still playing, as we would say in English, close to the chest, because they don't want others to steal their ideas. It's a very dubious approach, which I'm very critical of. So we're trying to reach out to everybody. I've given this talk in several places, and I show this line because I encourage us particle physicists, and not only medical physicists, to actually work in larger groups, to bring our best abilities and knowledge to accomplish what has not been accomplished. So in lieu of my summary, this is a group of my students and one postdoc, and I must tell you, I've worked on this entire project with many students, 2nd, 3rd, and 4th year. That's it, and one postdoc who came late. So this is essentially a testimony of, if you motivate young people, how much you can accomplish. This is my group and my TPPT group when we were closing the project last year in Lisbon is here, and I thank you for your attention.
Okay, thank you very much, Karol. It was very nice talk, very informative. Now we have time for questions. Perhaps you want to ask something?
Go.
How would you differentiate who is better off with the treatment of this type with the traditional one? What is the sort of criteria? What is process? Perhaps cost, position in geographic terms?
Oh, no, well, you're touching about too many aspects. Yeah, so let me just say that between protons and photons, physicians decided quite easily, depending on the penetrations and type of cancer. I have in my talk various pie charts which show what kind of cancer are treated which way. It's from essentially the experience. They know what to do. But for example, if you had anything related to the brain tumor, protons are always better. Just an example. Lungs, very similar. So there are many cancers that are obvious and many that are not. As far as political issues, that's too complicated. It's country dependent, it's continent dependent, it's all kinds of things.
Other questions?
Philippe.
This is also it's very general question regarding to what you showed at the very beginning, that about 50% of cancer patients are treated with radiotherapy. Do you have any guess, because I would guess it's rather a guess, not exact knowledge, is this because of the availability of this treatment, or so would we like it to be more? So should it be more than 50%, or is it just only 50% of cancers can be treated with therapy and not?
Okay, so I wasn't clear. 50% is actually radiation therapy in general, right? In other words, oncologists decide in 50% it's necessary, and I don't know if there are people who are being recommended for treatment and are denied of that treatment. I doubt that happens nowadays. So that is the number. 50% is essentially radiation is applied because it is needed by.
Radiation sensitive cancers are 50%.
That's correct. Well, radiation is sensitive. There are cases and cases. You have to really, it's a very, as you can guess, very complex issue. However, to first approximation, there is no proton therapy in this, right? Because out of millions of people who are treated with gammas, if you integrate over 20 years and it's 300,000, then it will barely show. You have to show logarithmic scales.
Using the prompt gammas, there are the techniques of the prompt gammas. There's a technique of Compton scattering of these 4 and 6 MeV photons from carbon used to measure the range. And the precision is something like 3 millimeters. So this is compares to the 511.
To what?
To the PET measurement.
So if you look at I have not shown the parameters of our PET scanner because it is being evaluated, and I don't want to quote numbers that we cannot have a clear demonstration of. But roughly speaking, our resolution, and I'm going to cut off my microphone and state it, it's about 2 millimeters, okay? So it's pretty good, and I think we can do much better, in fact. Much meaning maybe 1.6. There are indications that in some central portion of the so-called field of view, it can be as good as 1.6. It's a very good question what one would do for the prompt gammas, and it's called PGI, prompt gamma imaging, and the so-called SPECT, which is, again, to decipher for those who do not know, SPECT stands for single photon emission computed tomography, which is essentially taking individual gammas and image the area from or volume from which they were emitted. This is in this final design that I showed you, our ideas of how to have both spill and in-spill and post-spill data reconstructed. This is something that we need to simulate to really have a better understanding of how, specifically, what would be the pattern of collimators. That's really as you know from gammas, the collimation is the essential part. So we are getting there, but we haven't gotten that I can provide an answer.
Karol, you mentioned that the new center being built in Austin. What are the chances that your flash method will be implemented in this new center?
Fantastic question. Thank you. So, over the last 4 years, I've been trying to find partners. And, you probably do not know, but in Austin, they built a new medical school. it doesn't happen too often anywhere in the world, but it's called Dell Medical School because Michael Dell gave some seed money for that. So Dell Medical was essentially being formed as we were getting into it. So I had a great opportunity. Oh, let me just sell them this idea and tell them that we could find collaboration and work together. How naive and foolish of me. Nobody wants to hear it. The problem, I keep on repeating, the problem is that this is too disruptive. And in case you didn't know, you probably do, medicine is not about innovation. Medicine is about repeating the same over and over. Innovations have to be essentially brought in a push-button way from outside. But you obviously need money, funds, to develop it. So I think I'm just barking on the wrong tree, as the expression goes, to ask for money from centers that are, to begin with, not interested in this. Now, the reason that there will be a new center in Austin is actually a very simple one. MD Anderson makes so much money on this therapy that they are branching out to Austin. Austin is, one of the fastest growing cities in the US, and Houston is only 200 miles away, so why not create a new branch, and while we're doing it, let's just throw in Proton Center because, there'll be even more money from it. So when I was interacting with these people, I used the shame tactics by approaching some of the higher ups in the Dell Medical hierarchy, telling them, are you telling me that the most innovative radiation that is being now developed is going to be missed by what you pride on as the best medical research school in the country? They say, no, we'll work together. But I'm yet to hear from them. No, this is really, in case you haven't heard enough from me, this is a very frustrating problem for me. And I may in a year declare that it was a nice adventure and I'm done. Because I just cannot find traction with anyone who is truly interested in developing it. And it's very hard to convince developers, to venture capitalists, to develop a product like this because the market is tiny. I mean, maybe 100 devices would be good enough, maybe 200 devices. Well, that's relatively so-called peanuts compared to everything else. So it's a very tough proposition, yet there's a lot to gain. I mean, however, the gain from whose point of view? Patient's point of view. But nobody cares about patients.
So maybe it's a good point to stop this
No,
talk.
it's not.
Maybe you can continue offline.
Okay.
So let's thank Karol very much for his beautiful talk.
Thank you.
Okay. And this was the last colloquium this academic year, so we will see each other now in October, new academic year. So thank you very much.
Thank you.